Hi, what I have here on the bench today is an HP 8671A 2 GHz to 6.2 GHz microwave frequency synthesizer. I already have synthesizers and frequency generators in my lab that covers up to 2 GHz, like the HP 8642B back there in the corner, and 7 GHz up to 11 GHz, like the WaveTech 907 up there. The reason that I needed this frequency synthesizer is because I don't have anything that actually covers between the 2 GHz to the 7 GHz range. And this frequency synthesizer covers only up to 6.2 GHz, still a little bit shy of 7 GHz, but for what I do, and this should be more than sufficient. So I got this one on eBay and hopefully it works. Either way, I will open it up and take a deeper look inside shortly. In the same series, there is also HP 8671B and 8672A. Both cover up to 18.6 GHz as opposed to the 6.2 GHz range the HP 8671A covers. And this is achieved using an egg-tuned frequency multiplier. But the rest of the circuitry should be very similar to what you will find in this HP 8671A. Also to note is that HP 8671A does not have output leveling capability, which is a major drawback compared to the 8671B and 8672A if you require a precise output power. The output from the 8671A ranges anywhere between 8 dBm and 14 dBm depending on the output frequency, and it's fixed. So this figure in the service manual shows you that the output frequency versus the output power graph. And as you can see that generally the output power decreases as the frequency goes up. And there is a little hump in between the 3 and 4 GHz range. So anyway, before I open this unit up, let's fire it up and take a look at its operation. So to save some time, I have already hooked up the 8671A synthesizer to the 8566B spectral analyzer via this coax cable. And upon powering this up, it is defaulted to the 3 GHz range, and this is just a factory default. You notice that the not phase locked light is on. This is actually normal. At first I thought something was wrong, but reading the manual suggests that this would only disappear after you turn the output RF power on. So anyway, so right now this is set to 3 GHz, and as you can see we can adjust this. For example, the most significant, and we can adjust it by 100 megahertz, or you want it to go down, you can adjust by tenths of megahertz, and so on and so forth. But let's preset it to 3 GHz. And yes, the equipment are really loud, and unfortunately these older equipments, they need a lot of airflow inside the unit to keep it cool. So that is why it is so loud. But anyway, so let's take a look at the spectrum analyzer. So as you can see that we actually have two tones here, and one is the main tone sitting at 3 GHz, and this is actually a little bit out of range. So let's readjust the attenuation so that we set the reference level to, let's say, 20 dBm, so that we can bring down all the signal back to within the range. So let's do that. And so the first main tone, it's sitting at, let's see the power level here. Peak surge, it's about 11 dBm, and the harmonic tone is sitting at, let's do peak surge again, it's minus 8 minus 9 dBm. So according to the manual, and as we can see here, it says that harmonics is less than 15 dB. So clearly that is meeting the requirement there. But you notice that this, because the oscillator does have harmonics, and the harmonics are not totally suppressed. In fact, For the other models, as I mentioned earlier, the 8671B and 8672, they're using these harmonics to support a higher frequency range. So now let's center onto that 3 GHz signal and take a look at its characteristics. And I did some adjustment. I moved the center frequency to the middle of the display because these units are not phase locked together, so the 10 MHz reference for the 8671A is ever so slightly different than the 8566B. But anyway, so when I reduced the bandwidth, when I reduced the frequency span to 50 kHz and the resolution bandwidth to 1 kHz, as you can see here, you can clearly see the phase noise introduced by the phase lock loop, and which is a very characteristic of any PLL circuit. So anyway, so this is right now the signal is sitting at 3 GHz, and we can actually take a look at wider range. So let's go back to the 2 to 22 GHz range, and we're gonna say the stop frequency is 6.5 GHz. And we change the reference level back to 20 dBm again. So now let's adjust the frequency and see how that spectrum moves across the screen here. So let me just adjust the most significant digit: 3.1, 3.2, 3.3, 3.4. As you can see that as I am adjusting these the frequency range, the spectrum moves across the screen. So it looks like everything is working correctly. Of course, this unit also supports frequency modulation, so we can take a look at that as well. So now let's take a look at the frequency modulation capability of this 8671A. And for that, I have set up my WaveTech 395 to output a 1 kHz, 1 volt peak-to-peak sinusoidal signal into the FM modulation port of this 8671A. And right now the modulation is off. So and also I have the spectral analyzer set up to that the bandwidth of the frequency span of 10 MHz and at a resolution bandwidth of 10 kHz. And it's centered around 6 GHz, which is what the synthesizer right now is outputting. And so now let me turn on the frequency modulation. And as you can see that we indeed get a very characteristic FM modulated signal here. And you notice that the center frequency is slightly offset of the center. I'm not sure if that is something that this unit needs to be adjusted, but looks like whenever I turn on the frequency modulation, the center frequency is a little bit off. But anyway, so that's beyond the point of this demonstration. So while I still have this 8671A up and running, I want to take a look at the output power characteristics compared to the manual using my WaveTech power meter 1045. And because of the output could potentially be over 10 dBm, I purposefully added 2 3 dB pads to the input so that the reading here would be about 6 dBm lower than what you would expect if I put that directly onto the input. Also, the power loss over this very thin cable should also be taken into consideration. So let's turn the RF output on. Right now I have the synthesizer set to 2 GHz output, and if you remember from the manual we saw earlier, we would expect as we increase the output frequency, the power level would first start to drop and then increase a little bit and then further drop off. So let's see if that is what we are observing here. Now I turn on the output power, and we're sitting at roughly 9.4 dBm. Remember, we also have some cable loss here. And now let's start turning up the frequency. So let's do, as you can see, it's dropping. and right now we're at 2.5 gigahertz. It's dropping, further dropping, and now it's started rising. We're at 3.1 gigahertz, so it is indeed fitting the characteristics in the service manual, and now we're further increasing, and we started to drop off. So it jumps a little bit because I'm right now tuning the frequency. So now at the 6.1 gigahertz, we are about -2 dBm, and which translates into 4 dBm. There are a couple of dBms lost in the cable, and I think it's still well within spec. And while we're at it, let's also take a look at the output frequency accuracy using the HP5350B microwave frequency counter. And because of the maximum input, it's a 7 dBm max. So I'm also including these two 3 dBm pads here. And so right now, I haven't turned on the RF power yet. So let's first connect this. And so right now, the frequency on the 8678 is set at 5 gigahertz. So let's turn it on to see what we get. And we're getting only 400 hertz, roughly, off from the 5 gigahertz. So this is actually very good, considering how long this unit has been out of service. And as I mentioned earlier, once you tune the optimized frequency reference, they tend to be very stable over time, especially when the unit has been aged in service for a long period of time. And let's set it to 3 gigahertz and see what we got. Yep, so it's only about 220 hertz off. So now we see how this unit works, and it's time for us to open it up. So the top cover actually removes very easily with just one back-end retention screw, and now we can see the inside. At first glance, you will see this huge empty spot here. And no, it's not because anybody had taken anything out. This is a 8671A, and as I mentioned earlier, this one shares the same chassis as the 8671B and possibly 8672A. And both of those units have the output leveling and also the egg multiplier sitting at this area. So for those two units, this area is actually fully occupied. But for ours, since we don't have the output level control and we don't have the output the frequency multiplication, we only have this output isolator sitting right here. And just look at all these rigid coax and how meticulously they're bent to fit. And you can just imagine how expensive this unit was when it was first made. But right now you can pick it up for, just a fraction of the original cost. So I think what I'm going to do is I'm going to take some of the boards out and show you what they look like. And for some of the boards, I can see that we have quite a few screws to remove, and I probably won't do that in the video here, but I will take them out and take pictures and post on my website. So be sure to check my website out, and if you want to see some of the higher resolution photos of all the components within this unit. So now let's first discuss what all these components do and have a basic understanding, and then we will take them out one by one. So back here we have the digital circuit portion, and here in this under the this plexiglass we have some of the power supply unit and the YTO driver, the EEG-tuned oscillator driver. And then here we have some of the MN PLL circuitry. And here we have the phase detector and frequency divider and the voltage controlled oscillator. So that's essentially what this unit does. And basically remember, it's just a glorified frequency generator, and the output is not even leveled. So I think let's start from the top, and we'll take a look at some of the digital circuitry. And I had already removed the screw here, so we can just lift this up, and this should show us what is inside. The first board let's take a look at is the A2A7 interface assembly. And this basically tells you, has some indicators here. When it's powered up, it shows you whether the phase lock loop is in lock. And I just suspect these are just going to be some fairly standard. Oh, we have a cable here, so let's remove that as well. So these are just some fairly standard TLL circuitry, and each one of these chips, as you can see, these are actually all HP parts, so I don't know what they are off my head. But this is there's a little inductor here, and nothing too much to see here. So again, I'll put high-res photos on my website, and you can check them out. So let's put this one back, and let's move on to the next one. And here's our next board, which is the address assembly, and pretty much the same layout as the board before. So I think I'm not going to take all the boards out on this video to bore you. And again, if you want to see all the boards, we can you can go to my website. But we do have some. I call this a professional botch, because these are really not botch. These are actually designed to. You can see these have actually standoffs here. And so these are designed to be mounted this way, and probably due to the two-sided board constraints, they don't have space, so they have to, you know, have a jump wire here, and also have to have these kind of standoff. And interestingly, though, we only have one circuit in a socket, so not sure these were done afterwards or was before like that. And from the solder joints here, it doesn't seem like these are reworked, so it might just be originally like that. But not sure why this one is so special. It has to be socketed, everything else is not. Anyway, so let me put this back, and again I will take pictures and of the other boards, and we'll show you later. But we will move on to the section of the boards here, which probably is a little bit more interesting. And of course I forgot to put this cable back, so I have to take it out again and put it back. But otherwise it will not work at all. Okay, so now let me put this back. And one reason I really like these old test equipment in general is that they are meticulously designed, and they're designed for service. And as you can see, we have various test points. Everything is marked, and the diagram and everything. So you can, as an amateur, you can pick one up and has a reasonable chance to restore it to working condition if it does fail. Whereas the modern devices, you can buy one, and if it fails, it's basically just a FPGA and some highly integrated circuits. And the chance of you able to fix that as an individual is very low, no matter how knowledgeable you are. And in fact, the only way to fix that is either swap out the boards, or you have the specific chip that you can replace with. But for older units, it's just a joy to look at and to work on. So here we have all these test points. You can see that, you know, if you so desire, and you can check them out. But let's take a look at the power supply portion. And again, these things, you can see that they lift right off. And this is a positive power supply board. And we have this power transistor here, and you will see what this device is. Well, this is a crowbar mechanism. Basically, it's a silicon-controlled rectifier, and so this circuit monitors the output voltage, and when it's beyond, especially when it's above the specified voltage by a certain margin, it can start conducting and basically shorts out the output, so that to protect any downstream devices. And here we have the fuses, serves as the safeguard here. And so that's the positive regulator, and we also have this negative regulator. So that's the second one. So it's similar to the first one. So that's just for the negative rails. And the negative rail does not have the crowbar circuit. So now let's move on to the, I think it's the DAC, the digital to analog converter that is used to drive the IG oscillator. And everything is pretty much, discrete circuit here. And one thing jumps out at me is that if you look at these resistors here, these are actually precision resistors. These are 0.1, 0.2, 0.3 percentage of tolerance. And these are needed because we are doing a very precise DAC operation here. So these are really an art to look at. And as you can see here, made in USA. Of course, nowadays you can't find boards, you can rarely find anything made in USA anymore, but back then everything was made in the United States. And just to check a couple of date codes, and you can see that, I can't see anything right now here, but some of these are 82 and some of these are 81, so this unit probably was made after 82. So nevertheless, it's already over 30 years old, and it is still functioning, and which is even more amazing. So now let's take a look at the board for driving the IGs. And again, these are the boards. So each individual board, this is a power resistor here, and it's nicely screwed onto the board. So this one is the FM, no, not FM coil, sorry about that. This is the for the IG driver. So the last one in this section is the FM coil driver. And again, we have some transistors here on the heatsink and some adjustments. I just want to do a quick flyover before I close this up. And here, as you can see, this is the power transformer, and underneath there, tucked in, are a few power transistors for the power supply. And these are just the filter capacitors here. And here is our fractional phase lock loop section of the circuitry. And the overall phase noise of this unit is pretty much determined by the phase noise of this PLL. And of course, your phase ovenized frequency reference. And here are the boards we just saw before. And as you can see, these test points are clearly marked, so you can easily service this unit. And here we have the digital board section. And again, I showed you these boards. And I'll put more pictures. And what we didn't see is this IG portion and the yttrium iron garnet oscillator. And I actually had a very detailed look at one of the oscillators in my WaveTech 907. That's a while back, and I will try to find the link and link it below so you can take a look at what is the construction inside the IG oscillator. But I suspect it's rather similar, so I'm not going to take it out here, because this one does, you do need to remove the several screws, and the unit is actually quite difficult to remove this because all these rigid coaxes and the filters and the components here. So I'm not going to do that here, but I will again put a link there so you can see. So basically, this is the portion that is the main oscillator, and if we move over here, we will see that this is the other portion of that. This is the 2030 divider circuit, and this is the phase detector, and we have the VCO here. And interestingly, we can see this battery pack here. Believe it or not, this battery pack is still okay. And these are rechargeable batteries to maintain the setting of your frequency output when you power off the unit. And surprisingly, they're still working, but you can of course replace these. So here is that output isolator we looked at earlier. And the front panel really isn't too much to it. These are just basically handling your key switches and selections, things like that. And the other side basically are this is a rotary encoder, and is handling some of the digital display circuitry here. So that's kind of what is in this unit. Also, I forgot to mention that underneath there, you can also see this little adjustment hole here. That's actually a ovenized 10 megahertz frequency reference. We have seen quite a few over the years, and I have included many in my video. So if you wanted to see what they look like, you can also check out some of my other videos, but I'm not going to take that out. And here is a quick look at the reverse side of the unit after I removed the bottom cover. And again, as you can see here, the unit is designed for serviceability. As you can see, these measurement test point holes on this plexiglass, and everything is clearly marked. If you wanted to, for example, remove the YTO, you can follow the screws labeled here and remove them accordingly. And also you can see that we have another rigid cable, a rigid coax cable rather, connecting these 2 points, which is neatly laid out here. So that's pretty much what I wanted to cover for this video, and I hope you learned something new and enjoy the video. If you enjoyed the video, please give it a big thumbs up, and do remember to subscribe, share, and I will catch up with you next time.